Good day to you. In this video, I am going to explain analog to digital converter of dsPIC33E series of microcontrollers. I am going to explain only the special features, what are the latest advancements in ADC converters in this dsPIC microcontrollers. See, ADC stands for analog to digital converter. It gives a digital equivalent voltage of any analog signal. So that is a very short form definition of ADC. So let me briefly explain what is successive approximation ADC, which is being used in dsPIC series of microcontrollers. I think this is a popular way of converting any analog voltage into digital. Let me briefly explain what is a successive approximation ADC. Assume the bus voltage and the system voltage 5 volt and the incoming analog voltage is 3 volt. First, it will compare whether this voltage is greater than or lower than 2.5 volt, that is 50% of the bus voltage. If it is higher, then the most significant bit MSB will be set as 1. Second, if it is 1, then it will compare to 3.75 volt, whether it is higher or lower. If it is lower, it will set that second MSB will be set as 0, and this process goes on depending upon number of bits resolution required. So many processes will be repeated. So this is successive approximation ADC. This is easier to implement in microcontrollers. For more details, lot of videos are available in YouTube. You can refer some to understand what is ADC. For a simplicity's sake, let us assume this is a ADC block which converts incoming analog signal into equivalent digital signal or in a hex format of 12-bit accuracy. This is a conventional ADC block available in most of the microcontrollers. There is one ADC block, but it will be connected to many input pins. So one by one you can scan and then take the conversion. So all the switches are control switches. You can connect switch number 1 and then convert the analog voltage available at pin number 1. Similarly, you can connect switch number 2 and convert the analog voltage available at pin number 2. Likewise, one ADC block will be used in time wise, and then many analog voltage can be converted into ADC. This is a conventional type of analog to digital conversion available in almost all the microcontrollers of microchip. Let us speak a few words about sample and hold circuitry. The sample and hold circuitry take the sample of the incoming analog voltage. So the capacitor holds the time slice of the incoming analog waveform. The capacitor should be large enough so that it retains the charge reasonably accurate till the conversion process is over. And then moreover, that analog signal should be having less impedance so that it can charge the holding capacitor at early as possible. If there is a large input impedance from the signal, then this analog holding circuit will take more time to charge. So in that case, one has to put an amplifier to the analog signal so that the input impedance to charge the holding capacitor is less, and then measurement accuracy is maintained. So while designing the ADC, one should take care of the input impedance of the sensor circuit or the circuit which supplies the analog voltage. This is a block available in the dsPIC ADC controllers. There is one block which is a shared ADC which can be connected to any one of the pins, and then the voltage available at that pin can be digitized. Simultaneously, there are dedicated ADC blocks are available. Depending upon the part number of blocks will vary. So all these blocks can simultaneously measure incoming analog signals. This is an improvement recently done in dsPIC series of microcontrollers. So both options are available. There will be one shared ADC block, and then there will be few dedicated ADC blocks, so that few signals can be simultaneously measured at the snapshot of what is happening at that particular time at various points can be sensed. This may be very helpful in the power electronic circuits. For example, if you want to know the voltage of three-phase output, simultaneously you can measure all the three outputs and then take the voltage. So this gives a more accurate report of what is happening at the power converter level. This is the shared ADC. There is only one ADC block which will be shared between various pins. So one at a time, one analog signal can be digitated at one point at a time. Then you can go to next analog signal. Likewise, you can cyclically you can digitize any analog input. Also, you can do it in any series by controlling the switches. The switches are all selectable by software or firmware. So this is a dedicated ADCs. Number of ADC blocks depends upon the device number. So all these ADC blocks can simultaneously sample the input analog signal and convert them into digital format. So both the features are available, that is shared ADC and dedicated ADC are available. Microchip dsPIC ADCs have two features. One is single-ended ADC and another is pseudo double-ended ADC. Single-ended ADC input will be grounded and then you can measure with respect to ground, but incoming analog voltage will be measured or digitized with respect to ground voltage. So this is useful for unipolar voltages or DC voltages. There is another feature which can measure both positive or negative going voltages with respect to a reference voltage. The reference voltage will be always 50% of the supply voltage. If the supply voltage is 3.3 volt, that reference voltage will be 1.65 volt. So if it is going positive, negative, both can be measured. So this may be useful to handle AC voltage or AC current. So this feature is also available. You can program the IC or you can program the ADC to have a single-ended ADC or pseudo double-ended ADC. So here the single-ended ADC, that incoming signal will be measured with respect to 0 volt. In a double-ended ADC, that voltage will be measured with respect to VDC by 2. There is one feature called early interrupt. So once the conversion started, that a microcontroller knows the conversion will be over in such a period of time. Assume that conversion will be over in 10 microseconds from the start of the conversion. So it will give a interrupt, early interrupt. So the 10 microsecond you can use it to do other processes, so that when the result is ready, you can immediately pick it up. See, if the interrupt is generated after the conversion, then there will be some overhead in the interrupt service routine before you read the ADC result value. But here there is the interrupt is advanced a little bit, so that you can complete the overhead in the ISR, and then once the conversion complete, you can immediately read the value. So the interrupt is advanced a little bit, so that you can use the conversion immediately. There is another nice feature available in the ADC. So you take the incoming analog signal, convert it to ADC and give it to a comparator. The comparator compares with a reference value. So it will generate interrupt whenever the value is outside the range or within the range. Both the interrupt can be generated. This will be very useful in the power circuit. You can give the current input to the ADC. When the ADC value goes above certain value, then that interrupt can be generated and it should be possible to shut down the converter. So current protection can be very easily implemented using this feature. Oversampling of signal. This is another feature introduced in new series of dsPIC. What it does, it accumulates few samples. In this image shows that 4 times the ADC's converter all are added and can stored in the register. So you can choose the number of samples to convert and add. So this will work as a low pass filter. Assume the incoming signal is very noisy, there are some 1 or 2 spikes is there. By doing this, you can eliminate the spike. It will give you can calculate the average value. Assume you are taking 10 samples and adding all the values, and then you can divide the value by 10, so that it will work like a low pass filter. Apart from this, there are some other features. This is a 12-bit resolution. It can achieve 3.25 mega samples per second conversion rate. ADC can operate during CPU sleep and idle modes also. The ADC can be configured to 6, 8, 10 or 12-bit resolution. So this is the end of our video. Thank you for watching. If you have any help in programming these devices, you can approach me. Thank you once again for watching.